Hello guys, so in this video we'll be talking about 1.4 polynomial functions and rates of change. Okay, so first let's start with the general form of a polynomial. So let's say you have some polynomial p of x and the general form is the following. Okay, so you have p of x equals a sub n x to the n plus a sub n minus 1 x to the n minus 1 all the way to a sub 2 x squared plus a sub 1 x plus a sub 0. Okay, and in this formula, in this equation, a sub n must be a real number and n must be a whole number. Okay. Okay, nice. So actually, like when I meant, so here's like the coefficient of x. So a has to be a real number and then n must be a whole number. Okay, good. And so now if we look at this term, a sub n is the leading coefficient. Okay, and the degree of the polynomial is just n. So n is the degree of the polynomial. Okay, and you're supposed to write polynomials in order of degree greatest to least. So the degree starts with the greatest degree and then it goes down. So let's do some examples. So example 1. So let's say you have some polynomial, say p of x equals 3x cubed plus 2x squared plus x plus 1. So, and let's find the degree of the polynomial. And let's find the leading coefficient. Well, I'll just abbreviate as L/C. Okay, so pause the video and see if you can give this a try. Alright, cool. So, assuming that you have given this a try, let's get right into it. So the degree of the polynomial is the largest exponent of the polynomial. So in this case, the largest exponent is x cubed. So therefore, the degree is just 3. Okay, and the leading coefficient is just the coefficient of the highest degree term. So in this case, our highest degree term is 3x cubed, which the coefficient for that is also just 3. So the degree of this polynomial is 3, and the leading coefficient is also 3. Okay, cool. Let's do another example. So example 2. So now this time, let's say we have some polynomial p of x equals 5x squared plus 3x to the fourth minus 2x minus 3. And let's rewrite this polynomial in the standard general form. Okay, so again, pause the video and see if you can give this a try. Alright, cool. So remember, each standard form goes from highest degree to lowest degree. So we have to order this from highest degree to lowest degree. So the highest degree term is 3x to the fourth because that has the highest exponent out of x to the fourth. So the first term is 3x to the fourth, and then the next highest term is 5x squared, and then you have minus 2x, and then you have minus 3. And so p of x rewritten in standard form would be the following: 3x to the fourth plus 5x squared minus 2x minus 3. Okay, cool. All right, now let's move into extrema. And more specifically, let's talk about local extrema. So first, let's start with the definition of a local, or sometimes it's also called relative, but they mean the same thing. Local slash relative minima. Okay, so this occurs when the function switches from decreasing to increasing. Okay, and we have next local or relative maxima, and that's when the function switches from increasing to decreasing. So function from increasing to decreasing. Okay, so let's illustrate this with some examples. So let's say you have some graph that looks like this. Okay, so on this graph, we have 2 points of local extrema. So from this point, you can notice that the function goes from increasing to decreasing. So that matches the definition for local maxima. So therefore, this is also a local maxima. So this is just local max. And then at this point right here, the function switches from decreasing to increasing. And so this is a local minimum. Local min. Okay. And that's really all you have to know about local extrema. Okay, so now let's talk about another form of extrema, which is derived directly from this. Namely, let's talk about global extrema. So, global extrema. So, a global, and sometimes also called just absolute. Again, interchangeable. So, global or absolute minima. So that's the least of all the local minima. So if a function has more than one local minima, then the least of that would be the global or absolute minima. So least of all local minima. And similarly, the global or absolute maximum is the greatest of all the local maxima. So again, if you have several local maxima, the greatest of those is the global maxima. So greatest of all local maxima. Okay, again, let's illustrate with some examples. Okay, so let's say you have some function that looks like this. Okay, so you have 3 extrema, and so this one switches from decreasing to increasing. This is a local minima. This one also switches from decreasing to increasing, so this is also a local minima. And then this one goes from increasing to decreasing, so this is a local max. However, notice that we have more than one local minima. And of these, this one is less than this one. So this one would be called the global maxima or global minima also. So this is the global min or absolute, same thing. And even though we only have one local max, it's not the global maxima because notice how the function keeps increasing beyond this point. So this is not the maximum value of the function. The function continues to go higher than this point. So that's just a local maximum. Okay, good. Let's do another example. All right, let's say you have some function, some graph that looks like this, like upside down parabola, essentially. So here we only have one extrema, and this is a local max because it goes from increasing to decreasing. But this is also the highest value attained by the function, and therefore it's the greatest of all the local max, which there's only one. So this would also be considered the global maxima. So another way to think about absolute minima or maxima is absolute minima is the least possible value attained by the function, and global maxima is the greatest possible value attained by the function, given that the function changes from increasing to decreasing or decreasing to increasing. Okay, good. So now let's move on to the next topic. Okay, so the next thing is kind of like a little theorem, you could call it, maybe like a little lemma. It's basically saying that if a polynomial has at least two zeros, then it must have at least one extrema. Right, just a little theorem. And let's illustrate this. Let's explain why this has to be true. So again, if we graph it. So the first condition, the condition is that the polynomial has to have at least two zeros, right? So that means that it has to intersect the x-axis at least two times. So let's say we intersect the x-axis one time, okay, right here. So now, if it is to intersect the x-axis again, and we're going up currently, it has to come down at some point in order to intercept the x-axis again. And so that motion, you're going from increasing to decreasing. Because if you keep going up, you're never going to be able to intersect. So that's why you have to come down at some point in order to intersect. And so then right here, you change from increasing to decreasing, and therefore you have extrema. Namely, in this case, you have a local max. And this works the other way around too, though. So, for example, let's say now you're approaching from this side. So let's actually put the x-axis up here. So, okay, anyway, so let's say now you're coming down like this. Again, if you were to intercept the x-axis again in order to have two zeros, you have to come back up. So right now you're decreasing, but in order to intercept the x-axis again, you have to start increasing in order to come up. Because if you're to keep going down, you're never going to reach the x-axis. You have to come back up like this. And then right here, you change from decreasing to increasing, so you have a local mid. And in both of these cases, actually, they are absolute minimum and maximum as well. But yeah, hopefully this illustrates or this helps like build the understanding of why this is true. Okay, cool. And then we have like another little law, theorem, call it, whatever. It's saying that if a polynomial, if a polynomial, which I'll just abbreviate as POLY for short, has an even degree, then the global extrema are unguaranteed. So global extrema guaranteed. And okay, so again, I'm going to draw a graph so then I can illustrate this for you. So essentially, what does it mean for a polynomial to have even degree, first of all? So that basically means that the highest order power of the polynomial is even. So if it's a quadratic, a quartic, 6th-degree polynomial, etc., right? But let's also investigate the end behavior of an even degree polynomial. So, for example, if I have a quadratic function, the graph would look like a parabola. And so a parabola looks something like that. So notice how if x approaches positive or negative infinity, y is always approaching positive infinity, and vice versa. Let's say if this parabola was to open downwards, still a quadratic, right? Still a even degree polynomial, but again, as x approaches plus minus infinity, f of x always approaches negative infinity. And so that's the key thing about even degree polynomials. And also, what determines if the polynomial opens up or down? Well, in the case of a quadratic, the general form is ax squared plus bx plus c, right? And so I'm sure you guys have learned that if a is greater than 0, then it opens up. And if a is less than 0, then it opens down. And what is a in this case? It's the leading coefficient. And so this is true for all even degree polynomials, in fact. So essentially, if your leading coefficient is greater than 0, then the limit, which is just like another way of saying end behavior, as x approaches plus minus infinity, is going to be infinity, right? And then if your leading coefficient is less than 0, in other words, it's negative, then the limit as x approaches plus minus infinity is negative infinity, right? And again, this is true for all even degree polynomials. But this should help us answer a question, because if the limit, so if f of x always approaches infinity or negative infinity as x approaches plus minus infinity, then that means that at some point along the graph, it must go from increasing to decreasing or decreasing to increasing, right? So let's illustrate with the 4th-degree polynomial, so a quartic. So a quartic general shape of the graph looks something like that, right? So notice how it went from decreasing to increasing to decreasing to increasing. So it has to go, if it starts off at decreasing, it has to go to increasing. And so then that guarantees global extrema, or at least local extrema. We'll get to the global extrema part later on, but that guarantees local extrema, because you have to go from increasing to decreasing or decreasing to increasing. So right here, we have two local mins, and then one local max. Okay, and notice how this local min right here is also a global min, because it is the least of the local minima. Now you might be wondering, what if the graph looks something like this? right? What if you have two local minima, or if it was like flipped, then two local maxima, but same thing really. So let's say you have two local min, but they have the same value. And then you have local max right here too. But they have the same value, right? So then, which one of them is a global extrema? Well, as a matter of fact, both of them in this case would be global extrema. So I'll say both global extrema. Okay. And so that's why, and these are the only two cases that is possible, right? Either one is less than the other, or they're both equal. And so that's why, if a polynomial has an even degree, then the global extrema is guaranteed. All right. And then finally, our last touching point of this lecture is inflection points once again. So I know that we've already covered inflection points in a previous lesson, but let's just briefly revisit them in this video. Okay. So again, so what is a point of inflection? So point of inflection is where the graph changes concavity. Okay. So what does this look like graphically? Well, if you have some function, say something like that, the inflection point would be right there, because the concavity for this half of the graph is concave down, and then right here it changes from concave down to concave up, and so then that point at which it changes is the point of inflection. And like I said, I already talked about this in much more detail in a previous video, so if you are still kind of confused on what a point of inflection is, go visit that video. But other than that, that is pretty much it for this video. I hope you guys enjoyed. If you did, please hit the subscribe button and don't forget to leave a like. See you in the next video.